Thank you very much. It's really an honor to be here. And so in order to be consistent with the objective of this conference here, I thought that I would focus my remarks today on how advances in space technology can facilitate the collection of data that's relevant to sustainability, okay? So it's actually it's really interesting how David's talk and Zielko's talk and my talk are kind of building upon each other. So those of us in the planetary science area, I feel like we have a lot to offer this question. You know, David talked very clearly about the aspirational things of looking at worlds that have other properties. But the other thing about being a planetary scientist is that when you send an experiment to another planet, it's a lot harder than sending an experiment up into Earth orbit. So you're constrained by power and mass and data rate, and you have to think about how to make things compact and to compress the data. And so a lot of the things that are happening in Earth science today in terms of observations are things that planetary scientists have been thinking about actually for many decades, as long as we've been exploring. So, okay, let's see, I guess I can do this, right? Okay, great. So I went back and reviewed Laudato Si before coming here, and I really think that this is arguably the most eloquent articulation of the concept of intergenerational responsibility, and the idea that we ought to be leaving the Earth at least as good as we found it, even better. And quite frankly, we are failing miserably at this. And it's the fact that we're failing really that has motivated me to spend some time of my effort, you know, using what I know to try to help advance this problem of helping the Earth. And based on the discussions that we've had here today, I know that a number of you have similar feelings about this. So, so yesterday in the initial session, Jürgen Wren introduced the concept of planetary boundaries, okay, which are a framework where we can describe, the limits to impacts of human activities on the Earth system. And if you go beyond those limits, then the environment may not be able to self-regulate. And so for this region, we are approaching these limits, and for this reason, this is why we're moving from the Holocene into the Anthropocene. There is just no doubt about it that if the Earth cannot recover and self-regulate, we're not in the same geologic time that we were. But in order to define that, we need to collect as many observations as we can, and we need to monitor both spatially and temporally, and that's where these observations come in. So, so I don't need to convince anybody in this audience about the way that the Earth is changing and not in a good way. And but I will say that many of the events that change the Earth the most are the extreme events. Okay, it is the 100-year flood. It's the giant volcanic eruption. It's the asteroid impact, okay? And we need to be able to monitor those when they happen, as soon as they happen, in real time. But there are also monotonic changes that are occurring, such as the accumulation of CO2 in the atmosphere, which we also have to comprehensively monitor. And I wanted to talk about the fact that when we take these space observations, it is absolutely critical that we tie them to the in situ observations that are on the ground that give us context. And I think Francine's talk yesterday really showed us those observations and how they need to be compared. Okay, so here are just some examples the kinds of observations that we need from space-based environmental sensing. And I want to emphasize here in this presentation that these are illustrative. We can't be comprehensive on this, okay? But I will emphasize that such observations provide essential context, and that my paper that I put in the proceedings here talks about a lot of experiments that have been done on the Earth that have made these observations using satellites that have been developed over the course of decades, okay? And quite frankly, we can't keep doing it that way anymore because we are running out of time, okay? So we cannot take 10 years of planning and then launch an observatory and wait for the data to synthesize it. We need to be putting up sensors that make observations in response to changes that we're seeing and that we can replenish, okay, on a regular basis in order to be able to respond to what we're seeing in real time. Now here in this chart, what I've attempted to do to just move from tying kinds of observations that we need to actual classes of sensors that we would fly. So imaging and spectrometry, I won't go through all these, but atmospheric constituents, drought, food production, mass migration, et cetera. Radiometry is important to get the radiative balance, humidity, soil moisture, and then LIDAR and radar. I talked in my paper about how we can use a combination of altimetry and gravity measurements to separate out when we have sea level rise. There are contributions due to melting of ice on the land, but there is also a thermal expansion that's happening in the oceans because of the fact that the Earth is warming. And it is actually possible to tease out those two contributions. Okay, so how do we do all this? First and foremost, we have to be able to get experiments in space, okay? And this is just a table that I made with some costs of how much it costs to launch things, okay? So first of all, humans are a very cost-ineffective way in orbit to be making observations. If you want to send humans to space for some other reason and they happen to make observations while they're up there, that's great, okay? But there are more inexpensive ways to do that. For a long time, it cost $10,000 a kilogram, essentially, to get something into low Earth orbit, okay? And that actually didn't change for a while. And then SpaceX came along, okay? So with massive infusion of funding, actually, to the commercial sector, SpaceX was able to change the game in terms of bringing launch costs down. So, so if you can see up there, the Falcon Heavy now is down at $900 a kilogram, and actually with the Starship, Elon Musk thinks he's going to get down to $100 a kilogram, which I think that falls in the category of aspirational, but there's been a real decrease by a factor of 10, okay, in terms of what it costs to launch payload into space. So this has done some really important things. Well, first of all, it has allowed more things to launch, and we'll talk more about that, and Zielko actually addressed this a little bit, but it has also caused new players to come into the game, because for a long time we had governments with space programs as being the only ones who could provide access to space. Now we have commercial companies and nonprofits, okay? So it is opening up the space frontier to more players, okay? And, you know, something that we're seeing in our society in general is that there is a lack of trust in institutions. There's certainly a lack of trust in governments. There is a lack of trust actually in the commercial sector, but nonprofits actually have pretty good street cred, okay? And so some of the observables that are taken now by nonprofits and the Environmental Defense Fund launching MethaneSat, which is making global methane observations, is an example of a new kind of data set that could build trust with the public in terms of what the kind of observations that we're making. Okay, so let's go on. So we've also been able to make satellites smaller. So in the 1990s, 2000s, we had these gigantic Earth science observation platforms with many, many sensors, okay, that turned out to get into cost problems, technical problems, and were really challenging. Then we got to the point where we could do small sats, where small sats are about the size of a refrigerator, and we could put those into orbit relatively easily. And now we're in the realm of CubeSats, which were originally started mainly as a way to teach students, to give them experience. So if a student wanted to get experience in exploring space, they would do a sounding rocket experiment or a CubeSat. But the exciting thing that I want to talk about in terms of technology for CubeSats is that there are a bunch of innovations that are occurring that are making these very small platforms, and those are 10 centimeter, they're 10 centimeter cubes, and you can just put them together as many as you want. So 10 centimeters by 10 centimeters by 10 centimeters. And so, for example, solar arrays. The solar arrays are increasing in efficiency, so these things are not as power-starved as they used to be. It's possible now there are star trackers occurring that you can put on CubeSats that are both affordable and lightweight enough. And look at in the lower left-hand corner there, that is a pulsed plasma thruster that's about the size of a Lego block that can actually provide good attitude control on a CubeSat in orbit. Okay, and so so we're now putting up very, very small satellites that are actually able to make really excellent scientific observations. Okay, so this is an example. This is the Tropics mission here. Let's see. Okay, which is, this was the first CubeSat mission that NASA launched that was a real NASA science mission as opposed to a demonstration mission. So it was a set of 6 CubeSats at 550 kilometers altitude, and what it did is it looked at, it is a scanning radiometer, and it allowed to take profiles to look at the genesis of severe storms and precipitation patterns. And these 6 CubeSats had coordinated observations, and they updated every 50 minutes. So you could really look at storm intensification and movement. Okay, so this was a real step forward. Okay, next, I want to talk about satellite constellations. Now, Zeljko talked about this. On the upper right-hand side of that chart, this just shows the number of launches with CubeSats, not the number of CubeSats launched, but just the number of launches with CubeSats, and you can see how many are being launched now as a function of time. And I want to use Starlink as the example just because I had this nice picture that shows the first deployment of 60 Starlink satellites. These are not CubeSats, these are 200 kilogram spacecraft, but 60 of them were put up there. On the lower left is just a track of a Starlink satellite in the sky. This gets into the problem that Zeljko talked about the light source contamination from these. And there are currently 6,000 of them in orbit, 6,300 actually. with aspirations to put 42,000 of them in orbit, okay? They have been a godsend to people who don't have internet access, and they are helping farmers collect, use information to help them, know what their soil moisture is, how to plan for drought, when to plant, but they're killing ground-based observing on the Earth. So, it's a question here of we've got to be able to do a balance of putting them up there and then also trying to mitigate the harm that they cause to astronomical observing. Now, let me give a couple of specific discussion of types of sensors that we're using now. Some of these have flown in space. Some of them are flying actually in airplanes and are now suited to space. The one in the upper left there, that is a broadband imaging spectrometer, and something like that had flown in orbit, and that one there is being held in a hand. The volume of this has decreased by a factor of 10 while maintaining the same observing capability, okay? So this really changes the game for us. Over on the right-hand side there, that's a long wave infrared radiometer or imaging spectrometer, and that one actually uses pretty low quality components, but is actually able to make many, many repeated observations and get quality observations on the basis of signal to noise. And there's just some examples on the bottom there of applications in planetary sustainability, in coastal ecosystems. Yesterday, Donna talked about methane observations. Actually, this one uses a different method than the one that she talked about yesterday, but because there are several methods to do it. And then let me talk about the one on the right in ocean observations. The ocean, it's a very low viscosity fluid, and it changes repeatedly, and there are desires now to put up as many sensors as possible to do continuous monitoring in space and time on small footprints. And these technologies that we're seeing are enabling that. Okay, then next generation LiDARs. Okay, on the left-hand side there, that is an array where every pixel has a time of flight chip in it. Okay, and actually on the right-hand side is a map of Boston that was made in less than an hour with about 40 centimeters spatial resolution and 45 centimeters vertical resolution. And these things are now being planned to put into space. Okay, yeah. Okay, let's see. I think I'll go to the AI approaches for Earth science. We're using AI now to take these sensor data and do better things like better drought management, and then to actually to just finish up here, I just want to say more capable sensors in smaller packages, and you have planetary science to thank for some of that, but a lot of these sensors were actually developed originally in funding that was invested for national security. So, it's nice to be able to see that some real good is being made with those investments. So I'll stop there.